today's class. So in this class, I'm going to start with uh, matrices and determinants and their applications to metrics, to linear algebra.
Excuse me, sir.
হ্যাঁ,
Sir, have you taken the attendance?
না এখন অ্যাটেন্ডেন্স নিইনি,
আচ্ছা স্যার,
একটু
ঠিক
পরে নেব।
ঠিক আছে।
আচ্ছা, okay. So this is the last topic that we will cover in the first semester in mathematical economics. Now, mm, as economics, we often try to model our theory in terms of an equation or a set of equations. These equations can be nonlinear, but if you work with a linear equation system, then uh, understanding the nature of the linear equation system becomes much more easier. Of course, it results in some errors, but I mean, over here you have a cost benefit. The benefit is that it becomes easier to solve the system, easier to understand the nature, easier to see how changes affects the solutions. So these are the advantages. Computation becomes much more easier. The error, which is the cost of using a linear equation system, can be minimized uh, if you look at this part. Um, so suppose I'm looking at a graph like this. Or let us suppose that this is the a system that we are formulating, and let us suppose that we have the actual system is like this. So in that case, you can see that there's a very large component of error. Okay, sorry. But suppose we have a system like this, and we decide to model this using this. Yeah, again, there's an error. You can see over here, there's an error, there's an error over here. But in this case, you can see that the error, although there are errors, uh, it's not a huge amount of error as in the first system. Okay, so if you are working with a segment, I mean, suppose we are working with only this segment. Yeah, can we model this using a linear equation system? Yes. Look, even here, we can use, if we just apply it to a particular range, the error becomes minimized. So if you look at it, look at the entire system, it's non-linear and we cannot approximate it with a linear equation system, or in this case with a linear line, with a straight line. But if you look at segments, they can be modeled using a straight line. In this case, the entire economic system, the entire curve can be modeled using a straight line. Okay. So very often we used linear equation systems to solve, to model the behavior of agents in markets, in consumers, or we or people who are supplying inputs, or we can combine everything. So households are supplying inputs, they are consuming commodities, firms are buying inputs, they're supplying commodities, and so on. So when we study the linear equation systems, they come under the heading of linear algebra. Okay, now in order to understand and solve the linear equation system, we require the concepts of vectors, matrices, and determinants. Now, all of you know what are these, but still we'll have to go through them. Uh, Now, what is a linear equation system? Suppose we have a set of m equations, and in these m equations, we have n number of endogenous variables. These endogenous variables are x1 to xn, and we have some parameters. What are the parameters? The a's are the parameters, the b's are the parameters. So we have a11, a12 up till amn number of parameters, plus b1 to bm number of parameters. Now, some of these aij's may be zero also. So, for instance, we can have an equation in which this part, this equation, this term doesn't arise. Maybe this term doesn't arise. A1n is zero. So that is quite possible. Okay, now I've used two terms over here, endogenous variable and exogenous variables. What are these? Endogenous variables are variables whose values are determined from within the system. So over here, the values of x1, x2 will be determined from after we solve these equation systems. The exogenous variables are the parameters. They are the constants. They are determined from outside the system. They can vary, but they are determined from outside the system. In a Cobb-Douglas production function, for instance, the parameter A, alpha, beta, these are these are assumed to be constant, but they can vary as the technology changes. A varies, but the variation is not from within the system, it is outside the system. So when we use the Cobb-Douglas production function, we take the capital A to be given. Similarly, over here, the small aij's over here, the small bi over here are assumed to be given to us and assumed to be constant. Sorry. Okay. So if we solve these equation systems, we will get a set of ordered values s1 to sn. x1 is equal to s2, s1, x2 is equal to s2, and so on. These values satisfies all the equations simultaneously. So that means we have got m equations over here. All of them will hold if we substitute these values. Now, it is quite possible that the system has only one solution set, or it can have more than one solution set, 2, 3, whatever. In that case, we say that the system is consistent. And an inconsistent system is a system which does not have any solution. Okay. Now, I have used the word linear equation system. Now, what do we mean by a linear equation system? So, I'm writing a set of equations. So, can you tell me which of them are linear? Yeah. Which of them is the first one linear?
Say yes. The first
Yes,
one
sir.
is on linear.
The second one?
Yes, sir.
No, sir. It has XY term.
So that's the first one.
Okay. The third term,
No,
Not
sir.
linear.
okay, it has got square in these two terms. Okay. So only the first of them is linear. Uh, Sorry. This one,
So I guess it is linear.
see, if you have log y, this is a non-linear term. Okay. But what we can do is we can say that z is equal to log y. In that case, this becomes, okay. So it is, if you're talking about x and z, it is a linear equation system. But if you're talking about x and y, this is non-linear. Okay, so similarly, suppose if you have 4x square plus 3x plus 2y equal to 7. Okay, this is non-linear. But if we write this as 4z plus 3x plus 2y equal to 7, then this becomes linear. Okay. So remember, in this case, the solution is obtained in terms of z, x, and y.
So,
But yes,
so question. So out there, so in the second equation, so you wrote x square equals to y z, no sir.
this one,
So in the last equation,
this one,
so 4z, yes sir. So are you replacing x square with the z?
yeah.
So that means like so that should be like even x should be z root z, no?
No, I'm just writing this as z. But over here, we have to be a bit careful because, see, suppose I put, I mean, the value that I get over here, suppose I get z is equal to 2 and x is equal to 2.5 and y is equal to something. Suppose that solves it. This is not, this doesn't hold, right?
Yes sir.
So if I have a system like this, it may appear to be linear, but I have to keep in mind this constraint. Okay. But over here, this log y, this is not a very important constraint. I can always get z, and from z, I can simply find out what is Ez. That is equal to y. This should be natural log. Okay, so even nonlinear systems can, under certain cases, we can transform them to a linear system. See, over here, suppose I've got 4x squared plus 2y equal to 7. This is nonlinear, but I can write this as 4z plus 2y equal to 7. This becomes linear. Okay, so I solve for z and y. I keep y, but z, I take the square root. Okay. So even if you have a nonlinear system, sometimes it's possible to transform it to a linear equation system. This, it appears that we can transform it, but there are some problems over here. See, you have x square and x is coming. That is why we can't really transform it. from nonlinear to linear form. But if your equation is like this or like this, then it's possible to transform it to a nonlinear system. This also you can't really transform because you have to impose the condition. I mean, you can make it like this: az square plus bu bw plus cv equal to 0. You can make it. There's no problem with z or sorry. There's no problem with z and v, but w is so you have to impose this constraint. It cannot be any w. The w has to satisfy this constraint. So here you have the nonlinearity. But in these cases, it is possible to transform a nonlinear system to a linear system. Okay, is it clear or will I repeat it again?
Got it, sir.
Okay. Okay, now this is a problem that you have to solve. We have a set of n individuals and each of whom owns a quantity of different commodities. You have got m commodities and aij is the amount of ith commodity which is owned by the jth person. So what does a1j, a2j, amj represent? And if I add them, what does it indicate? What is the meaning of this?
So there are
So the
elements.
total amount of good owned by the J person.
Okay. Total amount of?
Goods owned by the J person.
Okay. So A1J is the amount of
Good one owned by
good one. This is the amount of good two. And you have got good M. All these are owned by. Can we add them up? Can we add them up like this? So basically, what are we saying? Let us say good one is tea. So I've got 2 bags of tea, let us say this is sugar, 3 kilos of sugar, and so on. Can we add them up to get something,
No, sir.
to get a scalar amount? So addition is not possible. So I can represent them in a vector form, in this form, like I've written over here, but not in an additional form. What does A11, A12 plus A11 represent? And is the addition valid?
Yes, sir, because here it represents the amount of good one owned by each person. Like E11 is the amount of good one owned by first person, then E12 is the amount of good one owned by the second person. So it will give the total amount of good one owned.
দাঁড়া, আমার লিঙ্কটা কেটে গেছে। না, এখন তো ঢুকেছি। 35, হ্যাঁ হ্যাঁ, সরি, আমার কেটে গেছিল। ঠিক আছে, সরি। Let's see, the recording is on. So when did I get disconnected?
It's been 10-15 minutes, I guess.
আচ্ছা, মানে আমি কতটা কভার করেছিলাম এই রো ভেক্টর কলাম ভেক্টর?
না স্যার।
এটা কভার করিনি। এইটে,
না স্যার, এত দূর তো
সরি, এই প্রবলেমটা এইটা থেকে
Sir,
করেছিলাম।
this was going on.
This was going on. Okay. So, okay. So let me repeat this. You have already answered the first question, that A1 is the amount of first good owned by the jth person. This is the amount of second good which is owned by the first person, and so on. Now, can we sum them up? The problem is that the units are different. Suppose this is A1j is T. So this will be in kilograms. Let us say this is milk. So this is in liters. Let us say the third commodity is bread. So it will be in number of loaves of bread. So the units are heterogeneous, and therefore addition is not possible. So the vector indicates the amount of different commodities which a person possesses. So let us see, if I'm talking about myself, what is the amount of the different commodities that I possess? Now, if I come to the second question, A11, etc., this is the amount of first good with person 1. A12 is the amount of the first good with person 2, and so on. So now the units are same, and therefore addition is possible. And if we add them up, we get the amount of, or rather the total amount of first good in the economy. Okay. Now, I have said that A1j, these cannot be added up because it's in different units. But suppose I multiply this by the price. So P1 A1j, this is the value of ith good with the jth person. So now everything is in rupees. So P1, 1J, P2, A2J, all these are in rupees, and it is possible to add up these amount. And the amount is the value of all goods with the jth person. It is given in rupees. Okay. So I'll return to this system, to this question again later on. But I hope you can understand all of it. Now, as I've said, that in order to solve the linear equation systems, we require knowledge of matrices. Matrices comprises a rectangular array of numbers. If there are m rows and n columns, the matrix is of dimension m into n, and we write it in this way. I mean, you know all of this, but I'm just repeating them. Uh, it's not necessary to have m into n columns. We can have just one row, in which case it is called a row vector. So you can see it has got n columns, but only one row. Or we can have a column vector, in which case we have m rows but only one column. Okay, so we write them as 1 into n, and this is m into 1 matrix. A square matrix is when m is equal to n. Okay, in this case, m equal to n equal to 3. So we have a 3 by 3 matrix. If see one of each of the components is given by aij. If I is equal to j, that is a11, a22, a33, and so on, these are called the diagonal elements. Now the linear equation system can be written in a matrix form like this. So we take out all the a values of a, the coefficients, a11 and so on, and we call this the A matrix. There's a column vector comprising the endogenous variables x, and another column vector comprising the exogenous variables b1 to bm, which we call b. Okay, now note that over here we have got n. This is, what is the dimension? The dimension is, this is m into n. This is n into m, and this is m rows but only one column. N rows only one column, m rows only one column. Okay, but if you multiply am, a into x, this becomes a vector which is of order n into 1. Okay, now I don't want to cover these issues because I'm sure that you know them. Matrix addition, matrix subtraction, scalar multiplication, some of the laws of matrix multiplication, association, and so on, commutation, and so on. So you can read them up in Chiang. I'm mainly covering Chiang's chapter 4 and 5. So you can read them up from Chiang. I'm not discussing them. Okay. Now, what I want to do is focus on matrix multiplication. Okay, so in matrix multiplication, In the equation system, we had written AB equal to C. What is C? C, an element in C is the inner product of the ith row of A and the jth column of B. Okay, so we take this row, we multiply this. So what we get is A11 B1 plus A12 B2, what we call the sum product, you can see. You're taking the product and then summing them up. And this is equal to C1's. If we take the second row and this one, we get C2. I've written the first and third row only. So this is this row. So A31 into B1 plus A32 into B2 and so on. So over here, note two things that firstly, I have used a matrix. I've used a square matrix. And second is I've used column vectors. Neither of them are necessary. We can work with a non-square matrix, a rectangle, when m is not equal to n. And instead of taking a vector, we can take B can be a matrix also. So A need not be a square matrix. B need not be a column vector. We can have a matrix also, and this can be a rectangular matrix instead of a square. Okay. So suppose we are taking a m into n matrix. Okay. When m is not equal to n, we have multiplied this by b and we are getting c. So what will be the dimension of b? Remember, b is not a vector. It's not a column vector, but b is also a matrix. In that case, what will be the dimension of b? See, this row has to be multiplied by this column. Okay. So how many columns are there? There are 3 columns. So after multiply this into this into this into this. So the number of columns over here must match number of rows. So number of columns in A must equal to number of rows in B. Okay, so how many columns are there in A?
Three.
No, let's talk about a general matrix. This is A m into n.
M.
The number of columns is n for Nagpur. So the number of rows must also be equal to n. Achha. Achha. Now we write the number of rows in the first. So this is n. And what is the number of columns in B? It
Sir,
can be
one.
any. There's no
sir,
restriction.
anyone. Anyone.
There's no restriction. So I can write k. In that case, how many rows will M have?
So we can have any.
Sir, M cross is
Okay.
So can you repeat the question again?
No, wait. Let me clear it up. Let me write down an equation system that will make it easier. So what is the order of this? I've got
8 to 4.
3 rows and 4 columns. So A is 3 into 4. Okay. So when I'm writing B, remember I have to multiply this. There are 4 elements over here. There has to be 4 elements over here in this column. Okay, so that means the number of columns in B must equal to number of rows in over here. So let me write. Okay, and this is the first column, so I'm putting it 4 1 1. How many columns do we need to we have? They can be any number. See, I can multiply this by this. I can multiply this by this. It's okay. I can multiply this by the first column, second column, third column. So it can be any number of columns. So I'm writing K. So there are no restrictions on the number of columns of B. So we say that you have got K columns. Okay. Now I'm multiplying this by this. So I'm getting one component. I'm multiplying this by this. This is the second component. This by this. This is the third. Can I have any component over here? No. So that means I can have only 3 rows. Only 3 rows are possible. Okay. But I can multiply this by the first column, this. Multiply this by the second column. So I get like this. So how many times can I multiply? So there has to be
K times.
k times. And this is, if I take a general form, I have got m rows, so this will be m. So what is the dimension? Dimension will be m into k. So the easy way of doing it is a m into n. The n will continue over here. You add k, n cancels out. So you have m into k. C will become m into k. That is the easy way of remembering this. Okay, but be very careful because whether the system is feasible or not, you can understand only if you look at the dimensions of the different matrices. Two. Okay. So you have to, the first problem is you have to write this in a linear equation form, in a matrix form. So what is the answer?
So
2,
3,
3, 4.
4, 7 minus 2.
So this is A. What is B? Is B a row vector or a column vector?
So column vector.
This is x1 and x2.
So 5 2.
This is. So if you look at this, what is the dimension? 2 into 2. This is 2 into 1. See, these two must match in order for multiplication to be feasible. Okay. And the resultant matrix is 2 into 1. This 2 comes from here and the 1 comes from here. So So what is the form over here?
Say 3,
It will be
4 minus
3, 4 minus 2,
3, 4 minus 2, then
2, 0,
2, 0
minus 3, minus 3,
minus 3,
4 minus 2,
4
5.
minus 2. So over here, a to 2 is 0. Okay. Yeah. Is the multiplication feasible?
No, sir.
Yes, sir.
Not feasible.
Why? It's a square matrix.
Sir, here 4 is not equal to 2.
Okay.
Um, feasible. And order of C will be 3 cross 2.
Yeah. Suppose it's feasible. What will be the order of B?
5.
5 2.
And C will be
4 2.
4 2.
4.
Sir, A will be M
Wait.
cross 5.
Yeah. So this will be 5.
This can be any number for it.
Yes.
And yeah. Now,
So 3 for it.
A3.
3 cross 5. 3 cross 2.
and this will be
2.
okay. So the rule in matrix is like this. This is the, you can see this is the rule. This must match. This is the rows in C's. This is the columns in the C matrix. Okay, so I'll end at this point. Again, matrix multiplication, there are some rules of it. I'll just state the rules over here. It's not much. It's easier to writing it. So just check it. ABC. So alpha is a scalar. So in the next class, I'm going to introduce concepts like identity matrix and so on. Do you know what is identity matrix, idempotent matrix, transpose?
Sir, I forgot. I knew it.
Acha, house. Okay. Anyway, we'll cover them in the next class. Okay, so I'm ending today's class. Thank you very much for attending.
Sir, attendance.
Yes, sir.
Yes, sir. Attendance. Then
Missed it.
একটু ছোট।
Sir, identity matrix ওটাই না A into A inverse equal to I.
Sorry, what did you say? A into I?
sir,
A
A
into
into
A
A
inverse equal
is
to
equal
I.
to I.
ওটাই কি identity matrix?
Now, A into I is equal to A. So it is the equivalent of 1.
Sir, he was telling about that A into A inverse is equal to I.
Oh,
Is
A
I.
inverse. A
হ্যাঁ,
inverse. হ্যাঁ হ্যাঁ
ওই আইটাই তো আইডেন্টি ম্যাট্রিক্স, ওটাই জিজ্ঞেস করছিল।
Yes, sir.
হ্যাঁ আচ্ছা, ময়ন্তিকা।
Present, sir.
আচ্ছা, মনজুর আলম।
Present, sir.
সুমিত টুডু।
Present, sir.
প্রাচী।
Present, sir.
প্রাঞ্জলি।
Present, sir.
আচ্ছা, প্রেমা দর্জয় প্রেজেন্ট। আনমোল। দীপাংশু।
Present, sir.
অনিরুদ্ধ। Saina was present. Swapnil was present. Bornini was present.
Present, sir.
Shreya Biswas.
Present, sir.
এই তুমি শ্রেয়া বিশ্বাস। আচ্ছা, সৌম্যদীপ প্রেজেন্ট। বৈভব অ্যাবসেন্ট। মাজ আলম। রিপ্রদামন। অর্পণ। সোমদেব। বিশাখা।
Present, sir.
সৃষ্টি।
Present, sir.
রোজমিন।
Present, sir.
খুশি।
Present, sir.
অদ্রিজিৎ।
প্রেজেন্ট স্যার।
অঙ্কুশ।
Present, sir.
সোনু মণ্ডল।
Present, sir.
সায়নী বোধক।
Present, sir.
নীলাদ্রি।
Yes, sir. স্যার এক মিনিট
ধৃতি?
ইন্টারাপ্ট করবো?
হ্যাঁ
স্যার বলছি যে আমি তো আগের দিন ক্লাস করেছিলাম, অ্যাটেন্ডেন্স শিটে এ নেই তো।
কে তুমি?
নীলাদ্রি।
সাড়া দিয়েছিলে?
হ্যাঁ দিয়েছিলাম, কিন্তু তখন ওই মানে একসাথে তিনজনের হয়ে গেছিল বলে হয়তো আপনি মিস করে গেছেন।
আচ্ছা আচ্ছা, ধৃতি, মোহর,
Present, sir.
আচ্ছা, আকিলা প্রেজেন্ট,
Present, sir.
দেবস্মিতা, দেবস্মিতা,
Present, sir. Present, sir.
শ্রেয়সী,
Present, sir.
আচ্ছা, শ্রীতমা,
Present, sir.
হ্যাঁ, পার্থিব, উপাসনা,
Present, sir.
আচ্ছা, সৌরজা,
Present, sir.
স্যার আমি প্রেজেন্ট স্যার, আমি
সায়ন্তিনী,
অনিরুদ্ধ স্যার, প্রেজেন্ট।
কে তুমি?
স্যার আমি অনিরুদ্ধ,
কে তুমি?
প্রেজেন্ট স্যার। আমি স্যার অনিরুদ্ধ বিশ্বাস, রোল নাম্বার 11।
Present, sir.
সায়ন্তনী
স্যার
প্রেজেন্ট।
অনিরুদ্ধ বিশ্বাস, রোল নাম্বার 11 স্যার।
হ্যাঁ দিয়েছি তো, দিলাম তো এখন তোমার, এই তো। আচ্ছা, স্বপন ব্যানার্জি,
প্রেজেন্ট স্যার।
আচ্ছা, বিদুষা, সৌপর্ণা দে,
Present, sir.
আচ্ছা, প্রার্থিতা মিত্র,
Present, sir.
আচ্ছা, দেব, মধুরা ঘোষ,
Present, sir.
Okay, thank you very much. I'll post this
Thank
lecture.
you, sir.
থ্যাংক ইউ স্যার।
থ্যাংক ইউ স্যার।
Yeah,
Thank
you
you,
may.
sir.
Happy Republic Day, sir.
Thank you, sir.
Yeah,
হ্যাপি রিপাবলিক ডে স্যার, থ্যাংক ইউ।
Yes, thank you.